This is the lecture for Chapter 8 for Stats 253 on using the t-distribution in hypothesis testing. Recall that the conditions for being able to use the normal distribution were that either you knew the standard deviation of the population, that is of the previous measurement, or the sample size was large. Okay, if those conditions aren't met, that is, you don't have access to the standard deviation for the population, you don't have that, or your sample size is small. I put that in quotes because there's a lot of ways to determine what's large or small, but for this class we're just practicing, and so we're going to practice using the t-values. Remember, these are similar to the normal distribution, but they're based also on the degrees of freedom, and that is the size of the sample minus 1. Okay, everything else is going to be very similar. You can use tables, or better, you can use R. But previously, when you used R with the normal distribution, you had the option of including the mean and the standard deviation from the original experiment, so that you did not have to change your test value into a z-value. For the t-distribution, you don't have that option. Everything has to go into the standard distribution. So you have to take your test value and you have to convert it into a t-value. And the equation looks very similar. Okay, and again, you can do that in R, and you can look in the tutorial to see how to do that. Remember to use enough parentheses to make sure that the square root of n is dividing s and not dividing that numerator. The ideas of one and two-tailed tests are the same. It doesn't hurt to state them again, then you don't even have to think about them after this. For a two-tailed test, your alternative hypothesis is written with a not equal sign. Then you're going to have two tails, and each tail will have an area of alpha over 2. For a left-tailed test, the alternative hypothesis is written with a less than sign, and the area of the tail, there'll only be one tail, it'll be on the left, and it will have an area of alpha, all concentrated in the left tail. And then similarly for a right-tailed test, the alternative hypothesis is written with a greater than sign, and the area of the tail on the right will be alpha. And here's an example for a right-tailed test for t-distribution. In this case, we're looking at the advertised nicotine content of cigarettes, and it was advertised at 40 milligrams. We're going to take that as the null hypothesis, that the nicotine content in cigarettes is 40 milligrams. Okay, so this is our a priori value. Then somebody makes a study of 15 cigarettes and finds a mean of 42.6. Right. So the idea of that appears in the alternative hypothesis that the nicotine content is greater than 40. Remember, at this point we don't use the exact value of test, exact mean from the test of 42.6. Okay, so we want a 1% probability of making a type 1 error. Okay, that means your alpha is 0.01. And this is a one-tailed test. It's going to be a right-tailed test. That means the area under that right tail is 0.01. Okay, you can look it up in some tables, or you can use R, which is better. So this is going to be a critical value on the right. I'll put that just to give it a name. And it's the same terminology as before. Here's your t-distribution. The base word is t, and I'm going to use q to get the value of t at the edge of the critical region. So I have to give it the error, which would be 0.01. Right, this is a right-tailed test, so I want the lower tail equal to false. But there's another parameter for t-distributions, and that's the degree of freedom. So degrees of freedom equals, and you can give it an exact value, or you can write n minus 1. How many were in this new study? 15 cigarettes. So it's 14 degrees of freedom. and I would go ahead and write lower dot tail equals false. Okay, that's it. And from that you will get that critical value on the right, which in this case is 2.624. Okay. Now, because you have to use standard deviations with t, you have to take that test value, and the test value was 42.6, and you have to change it into a t value. So 42.6 minus 40 divided by 3.7, which was the standard deviation of the sample, divided by the square root of 15, and that came out to be 2.7215. Okay, what is the critical value is 2.624, and now my test value is 2.725. It's a right-tailed test, so this is out in the critical region, and it would lead to the rejection of the null hypothesis.